Hello everyone, welcome to Mount San Antonio College. This is our week 13 gas tungsten arc welding lecture. And what I wanted to talk about in this lecture is gas tungsten arc welding. Just as it's spelled here, gas tungsten arc welding. It started in the 1930s, 1940s. Two gentlemen began the process, Russell Meredith and V.H. Paul Litka. I guess I kind of wanted to start just by showing you a torch, the actual gas tungsten arc welding torch. You can see on this particular torch, there's a power cable, but there's also an inlet and an outlet for the water in and water out in order to keep the torch cool. So this is just an example of a water-cooled torch. The other item, as far as the ceramic cup and the cap and such and so forth, we'll talk about in just a moment. But what's really nice about this weld process is that it's very precise, very concentrated type of welding. We certainly weld a lot of aluminum and stainless and Manels and the Inconels. It's used quite a bit in the aerospace industry, but also throughout the welding industry itself. Once you use the process, you see the advantage of it, particularly with thinner metals and how well you can control the heat during the welding with it. So let's start off with a few things. There's a couple of terms. Gas tungsten arc welding, which is what we just talked about. Also the term TIG. Sometimes people refer to it as TIG welding, and that stands for tungsten inert gas, because there was a time when they were only using inert gases for the backing gas. And we've gotten away with only using inert gases. So the technical term for this welding process is gas tungsten arc welding. That's what you'll see on all the welding procedures or anything formal with regards to this process. But nevertheless, this is a slang term, the word TIG. Another slang term is heliarc. In the early days, they were only using helium as a backing gas, so they were calling it heliarc or helium arc welding. But these three terms, they really all mean the same thing. It's referring to the same process. And again, this is just a more formal way of talking about the weld process itself. The welding process uses a backing gas, and that also is fed in through this cable here, and it's used to provide a backing gas in order to keep the nitrides and the oxides that are in the air from attacking the molten metal. Our breathing atmosphere is 78% nitrogen and 21% oxygen. So the nitrides and the oxides in the air, the minute you get something molten, it wants to attack it. So you have to have a backing gas of some sort to protect the nitrides and the oxides from just contaminating the weld. And that's the purpose of the argon and the helium. These are definitely the most commonly. There's other gases that are used, and there's gases that are not inert, which is why we have another formal name for this welding process. But in the grand scheme of things, most of the welding that you do with this process, you're either using argon or helium as the backing gas. The helium gas is more dense and you get better coverage with it. It's actually 10 times heavier than the helium. You may be asking, well, why go to helium if it's that dense and it provides that well of coverage? And that's because helium gives you more penetration and allows you to penetrate on the thicker metals. You know, in my almost coming up on 40 years of welding, I've only used the helium gas once, only once. I was welding a real thin piece of aluminum, and I used the helium gas. But that doesn't mean if you end up in a fab shop where there's a lot of thick aluminum, you would be using quite a bit of helium, and also that with other alloyed metals that you may be welding. It's when you get into the thicker metals that you introduce the helium gases. couple of terms here that I wanted to talk to you about. The weld torch itself is either air or it's water cooled. Now the water cooled has a reservoir that has water in it, and it's cycling it around through the torch. Because if you're welding all day, this torch can get extremely hot, and to a point where you can't even put your glove on it. That's how hot it will get. And that usually only happens when you're using the air-cooled torches. When that happens, you just have to set the torch aside, let it cool down, and then when you're able to hold it into your hand without burning yourself, then you can go ahead and start welding again. But with the water-cooled torches, with the reservoir of water and it being cycled through, you can literally weld all day. You can weld 24 hours a day with it, as long as you're keeping water in the reservoir and cycling it. The other thing that I wanted to talk to you about were the pieces of the torch. With gas tungsten arc welding, we're talking about a collet body, a cap, and a cup. So I wanted to take just a moment and show you those items. This is the cap right here, and this is a piece of tungsten. You'll notice that on this piece of tungsten, it has a red end, and we're going to talk about that in just a moment, so keep that in mind. But this is a piece of tungsten. Also in here is a collet, and I don't know if you can see real close, but there's like slots there in the collet itself, and that's what actually holds the tungsten in place. I'll demonstrate that in just one moment. And then also we have a ceramic cup and the actual collet itself right here. So inside this collet body, it's tapered in like a V shape at the base of this, inside this hole right here. So as this collet goes into the collet body, you can see the slots on it right there. And as it goes in and you push on this, as this gets pushed, it grabs onto the piece of tungsten. So this is a very, very easy concept if you just kind of watch what I'm going to do. So the collet goes into the collet body, and then that gets screwed into the torch. That should be your first move when you're putting this torch together. The next move is flexible, but you can put this piece of tungsten in. That being said, let me say this. This is worth repeating and actually showing one more time. This collet and collet body have to be the same size as the tungsten, whatever size tungsten you have, because they sell these in different sizes. And what I'm trying to suggest is that if I have a 332 collet body and a 1/8 inch collet, when I put this together, it won't be able to grab onto the tungsten. I won't be able to tighten, because what ends up happening is that this cap goes on and it gets tightened and it pushes onto that collet, pushes into that tapered hole, and that's what actually holds this piece of tungsten in place, that push onto the collet itself. But just keep in mind that this collet body and the collet have to be the same size, and it has to be the same size as the tungsten that you're using, because this tungsten comes in different sizes. All right, so your first move is to put the collet and collet body together, and then you can get the piece of tungsten in, and then the cap can go on. Now again, when I screw into this cap pushes onto that collet, and that pushes it into the collet body, and that's what holds the tungsten in place. The moment that I back away on this cap, it loosens that collet in the collet body and allows me to move it. And then the ceramic cup goes on. So we adjust this tungsten. It's about 1/4 inch outside the ceramic cup. And like that would be ready for welding right there. How I hold the torch? Well, there's some flexibility. Some people hold the torch like this if they're walking the torch. But if I'm being very precise, I take my peace sign and it goes right over the cap itself, just like that. And then my thumb goes beneath the torch, just like that. I also have my elbow up against my body like this. Keep in mind, if I move this elbow away from my body like that, I get a lot more leverage on this torch. Now this is my pivot point up here, which means just the slightest movement, I get a lot of movement at the end of the torch. And with gas tungsten arc welding, I want to minimize that. And so my elbow goes against my body and I'm right here. It's a very precise. I usually have a filler rod as I'm doing this, but I do the weld in a very precise way. So that's kind of an introduction to the torch itself. We can talk about the tungsten for just a moment. The tungsten comes in different sizes. Again, make sure the collet and collet body are the same size as whatever tungsten you have. And there's 1/16, 332, 1/8 inch, all the way up to 1/4 of an inch. And I'm talking about the diameter of the tungsten itself. You can imagine a 1/4 inch in diameter piece of tungsten. You'll be able to weld some fairly thick pieces of material with it. The tungsten melts at 6,152 degrees Fahrenheit. The interesting thing about that is that this welding process is somewhere between 11 and 14,000 degrees Fahrenheit. So you might be asking, how is that possible? Why is it that the tungsten doesn't melt as you're doing the weld? And it's because of the heat transfer, how quickly the heat transfers. An easy way to explain it is that an ordinary match is 3,000 degrees Fahrenheit, and a piece of aluminum melts at 1,220 degrees Fahrenheit. So if I take that 3,000 degree match and I put it right on the corner of that piece of aluminum, even though that piece of aluminum foil, if you will, it's less than a 16th inch thick, it won't melt. And the reason why it won't melt is because the heat transfers through the aluminum quick enough where it will just transfer it and it won't actually melt itself. And same thing applies here with the tungsten. Keep in mind that tungsten is non-consumable. When you're first learning the process, you kind of dip it into the molten puddle. Some people ask, well, how close can I get? You can get as close as you want, as long as you don't touch the tungsten into the molten puddle. If you do that, the molten puddle will jump onto the tungsten and it gets contaminated. So you'll have to go and you'll have to grind another point onto the tungsten. That being said, I wanted you to keep in mind, when you're grinding tungsten, make sure you're using a tungsten-only designated grinder. You should not be using a grinder that's used to grind mild steels, other types of steels onto this grinder, because you will grind those other metals right into your tungsten as you're grinding it, and it'll create like a sparking effect in the tungsten. So we always designate a specific grinder that's used only for tungsten, and that's where we actually grind a point on the tungsten itself for the welding. The tungsten, you can get pure tungsten. The end of it is green. Typically we use this for aluminum. So if you're welding aluminum on AC current, we do use the green, we use the pure tungsten. But if you're welding all these other, the Inconels and the Manels and the stainless steels and regular carbon steel, we usually get into an alloyed tungsten. And the reason why they alloy them is because they're easier to start the arc, it resists contamination, and you can carry higher currents with it. So alloying the tungsten, they found out over many years that it made it more of a feasible way for the welder to work. Very, very commonly, we use 2% thoriated tungsten. and that is a red band on the end of the tungsten. If it's 1% thoriated, it would be yellow, and it's either thoriated or zirconia are the two alloys that they use, and it would be brown if they were using the zirconia. Most of the welding that I've seen in the field, most people use 2% thoriated because you can use that on all metals, including aluminum. You get these advantages, plus you can use it to weld anything with alternating current, which would be aluminum. Okay, a couple things to talk to you about. With this welding process, there's no flux inclusions. There's no corrosion from flux. There's no splatter, no spark, no fumes. The alloying elements in the metal are not burned away. And you're not adding carbon to the weld. So this welding process, you end up with a more stronger, more ductile, more corrosion resistant weld than any of the other welding processes. That's how precise this particular type of welding process is. So I wanted to take just a moment and talk to you and mention the advantages. In this class, we're going to be welding aluminum, we're going to be welding mild steel, and we're going to be welding stainless. So you'll get a variety of different types of metals to weld and what it looks like. So here's some of the advantages. The weld is very clean, very good quality. The arc heat is intensive and it's highly concentrated. There's no smoke, no fumes, no splatter or slag. And that's remarkable. It's remarkable that you can do a weld and then send it right to the paint shop. Or if it doesn't need to be painted, like aluminum or stainless, it's literally, you're done. You're finished with the weld. On the alloyed steels, it's not going to rust. So it's really an advantage. The weld zone is highly visible as you're doing this. And the weld chemistry itself can be controlled because it is so concentrated. What's the disadvantage? Well, it's kind of a slower weld other than the other processes when we're talking about flux core arc welding or MIG welding or shield metal arc welding. It is a slower process. You have to have a backing gas with this to protect the molten puddle from the nitrogen and oxygen that's in the air. The nitrides and oxides are trying to attack the molten puddle. And the equipment is expensive, more expensive. You have the cost of the inert gases. So that disadvantage means that you actually have to have a cylinder with you. So you got to imagine, I'm not just picking up the machine and moving it somewhere and setting it down and plugging it in. I've got to bring a cylinder with it, and I've got to have a backing gas with me as I'm doing this particular type of welding. And what's known in the field is highly skilled welder. So you've got to be a little bit higher skilled, which is why we actually wait to do this process at the very end of the course. It's the last 3 welds that we do, in that the oxyacetylene, shield metal arc, flux cord, the MIG, all those are going to give you eye-hand dexterity, if you will, and then enter into this process, which is the more difficult of them, and to put all your skills together in order to produce the weld. The other thing with this particular process, particularly when you weld aluminum, is we get into something that's called square wave. And on the square wave machines, they actually allow you, and this is alternating current welding aluminum, they actually allow you to actually dial in how much of the half wave of the alternating current, how much of it is on the electrode positive and how much of it is on the electrode negative. And what this does is it controls the heat penetration onto the metal itself. So when you get into these 20 thousandths, 30 thousandths aluminums that they use in the airplane industry, it's extremely difficult to weld those thicknesses. And this square wave technology entered in and made it a lot easier for people to be able to weld those thicknesses. It's not uncommon, you know, especially if you're talking about an airplane, you get into the material engineering part of it, and, you know, every pound of material that they cut off that airplane, that they don't use on the airplane, I should say, you know, it's less gas, less fuel. So they need the strength in order to handle the live and dead loads of the airplane. In the higher strength areas, though, they typically use titanium, like in the landing gear and things like that, but the majority of the rest of it is all aluminum. And that thickness of the aluminum is a very, very important decision that the engineers make during the design phase of it. Okay, so that kind of covers everything that I wanted to talk to you about for, I typically say TIG welding. I normally call it TIG welding. But it's gas tungsten arc welding. That's normally what the information that I like to talk about. My last comment to you is on stainless, because we are going to be welding stainless as part of this process. And the interesting thing on stainless, just for something to keep in mind, I can take a regular mild steel, and the moment that I enter into 12% chromium, once I reach into the 12% zone of it, I enter into the stainless families. And that's where you get into trouble with stainless. And that is overheating the stainless. Overheating stainless. When you get above 1333, 1333 degrees Fahrenheit, the carbon in the material actually combines with the chromium and it forms chromium carbide. And chromium carbide rusts. It will rust. So what I'm trying to say is that if you have like a half-inch thick half-inch thick pipe, and you just weld the living daylights out of it, and you take no consideration to the amount of heat that you're putting into the weld joint itself, you will get this chromium carbide, and the joint itself will rust. And so it's an important thing to keep in mind. Typically in welding procedures, when you're welding stainless, they hold it to 500 degrees Fahrenheit, meaning you run a pass, and then you typically have a temp stick. It looks like a crayon, but it melts at 500 degrees Fahrenheit. And you just mark it on the weld right next to the weld zone. And if it melts, that means you're above 500 degrees Fahrenheit. And then if it makes like a chalk mark on it, you're not at the 500 degree mark. So then you can go ahead and continue welding. So it's not uncommon when you're welding stainless and you're welding multiple layers to have a temp stick with you and to check it. Another thing to keep in mind with stainless is you don't want to use carbon steel, like carbon steel brushes, carbon steel wire wheels, so that you induce more carbon into the weld. So anytime you're welding stainless, we mark everything with a white mark, with a white paint mark. So stainless steel wire brushes. So you want to get a stainless steel wire brush and mark it with a white paint mark. Or definitely if you're going to grind it, that grinding disc should be marked with a white paint so that you're only using that on stainless steel, where you're not using that same grinding disc over here on mild steel, grinding, then coming over here and grinding it onto the stainless, because you will induce carbon into the weld and increase this possibility of getting the chromium carbide. Stainless can be welded, and it's very easily welded. It's not too difficult to do. It's a little bit more of a wetter look to it than mild steel. But you do need to keep in mind about this, getting it too hot and watching the intermediate temperatures as you're doing the weld. So I think that'll complete the lecture, and thanks for listening, everyone.